Hello, this is Dr. Zoon, and today we're going to be working with straws and pipe cleaners and making straw structures. We're going to be constructing several different solid geometric structures: the tetrahedron, the hexahedron, the octahedron, the dodecahedron, and the icosahedron. We'll also be looking at several other structures that are made from triangles, squares, and other geometrics. Let's get started! Today we're going to be using pipe cleaners and straws to assemble our structures. The straws we want to use are just a little larger in diameter than our pipe cleaner. The straws will easily accommodate one leg of a pipe cleaner and will also accommodate two, and in some cases even three, legs of pipe cleaners. Kids, when you're using pipe cleaners, be very careful with the end of the pipe cleaner as it has a sharp point. Let's begin by talking about structures, like the familiar triangle. The triangle, of course, is a geometric structure. It has three sides, and in a structure, each of these sides would be considered a member. Each of these sides is a different member. In a structure, each member will have different forces acting on it. There's two major forces that act on each member in a structure: compression and tension. We can demonstrate tension as being a pulling force, as I am pulling on each end of this pipe cleaner. Compression, on the other hand, is where I'm pushing in on each end of the pipe cleaner. There's a couple other forces that can be occurring in structures. Those forces are torsion and shear. In our example with a pipe cleaner, torsion would be a twisting motion of one or both ends on the pipe cleaner. We could twist in either direction, and that would be a torsion force. The other force, shear, would be in our example of a pipe cleaner. If the pipe cleaner was sitting across two boxes like this, and a force came down in a perpendicular motion to that member, this would be shear force. A shear force on a flexible member will just cause the member to flex. However, if we apply a shear force to a stiff member, it won't bend or flex very much. If we apply more force, it will break. Yeah! In the triangle, we have two major forces at work. We have compression on the two sides of the triangle, and we have tension on the bottom of the triangle. As it turns out, the triangle becomes the basis for almost all major construction types. Let's begin building some structures, and let's start with the triangle. To build the triangle, we'll need 3 straws and 3 pipe cleaners. To begin the construction of the triangle, we insert the end of a pipe cleaner into one of the straws until it's about half the length of the pipe cleaner. On the other end of the pipe cleaner, we put a straw onto it. We take a second pipe cleaner and insert it into the end of one of the straws until it's about halfway down that pipe cleaner. And now we can bend our first joint like this. The third pipe cleaner we insert into one of the free ends of the remaining straws, about halfway, and then bend it and put it in the free end of the other remaining straw, and bring the two ends of the straws together, making our joint. So now we have a triangle structure. The easiest structure to build from a triangle that's a three-dimensional structure would be a pyramid or a tetrahedron. The tetrahedron is a solid geometric structure composed of 6 sides and 4 faces. Let's see if we can build one. To begin construction of the tetrahedron, we will take one pipe cleaner, fold it in half, like this. Now we'll find the center of this folded pipe cleaner. We'll hold it with our thumb and index finger while we take one leg and wrap it tightly around the other, like that. We'll need to make 4 of these corners like this. So we'll take a second pipe cleaner and do the same process. We'll fold it, find the middle of it, wrap one leg around a couple times, and bend it. Into 90-degree angles. Once we've completed the 4 corners, we're going to take one corner and we're going to put straws on each leg of the corner. We'll take a second corner and insert it into one of the straws attached to the first corner, and we'll add straws to the other 2 free legs. We'll take a third corner, insert it in one straw from the first corner, and also in one straw from the second corner. We'll also add one straw to the free leg. To complete the tetrahedron, we'll take our 4th corner, we'll put it into the 3 free straws. Now we have a tetrahedron. There are 6 sides to the tetrahedron. Let's count them. 1, 2, 3, 4, 5, 6. There are also 4 faces to the tetrahedron. Here's one face of the tetrahedron. Here's another face of the tetrahedron. Back here is a face of the tetrahedron. And then, of course, we have one face which is on the table of the tetrahedron. We'll do a little experiment with our tetrahedron. We'll place a load on the top of the tetrahedron by pushing down with our hand, and let's look at the result. As we push down, the straws, or the members of the structure, will flex or bend, but the structure will stay pretty much intact. Again, what forces do you think are acting here? In the members that are going down, we have compression. We have a force pushing down or inward on both ends of the upright members. At the bottom of the structure, around the base, when we push down on the top, the force translates into a tension force, causing each member at the bottom, causing each member at the base to come under tension or be pulled apart. Let's build another structure, a cube, which is actually called a hexahedron. The hexahedron has 12 sides and 6 faces. For the hexahedron, we'll need 12 straws and 8 pipe cleaners. Again, we will need to bend each pipe cleaner into our standard three-legged formation. Once we have finished bending the pipe cleaners, we will start constructing the hexahedron by adding straws. And putting corners where corners should go. There's no particular order in doing this. We just want to be sure that we end up with a geometric solid that looks like a cube when we're finished. And there we have it, a hexahedron. The hexahedron has 12 sides. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And it has 6 faces. There's one on the top, one on this side, one on this side, one on this side, one on this side, and of course the bottom face. That makes 6 faces. Let's see what the difference between the hexahedron and the tetrahedron structures are. If we place a load on top of the hexahedron and push down on it, it tends to just go kabunk. If we place a load on the tetrahedron, we can see that it flexes, but it doesn't lose its general structure. If you ever noticed in building construction, many of the shapes that are used are triangles. Now, the side of the house may look like a square or a rectangle, but the roof, which supports a major portion of the structure, is built from triangles. In fact, let's take a look at an actual model of a roof structure, like this one. This is a model of a roof. You can see inside of this roof is made of several triangular structures within each large triangle within the roof. So roofs are made of several triangular structures. Let's get rid of this thing and talk about our straw structures once again. The structures that we've been putting together so far have each had 3 members coming out from each corner. We'll need 2 pipe cleaners for each corner. We'll take the 2 pipe cleaners and put them together in the middle to form an X. Where they come together, we're going to twist one around the other. So it looks like this. With the other pipe cleaner, we'll wrap it around once as well. We bend the end of each leg back in towards the center. And this completes our corner. This type of corner with 4 legs will allow us to make a octahedron. The octahedron has 8 faces and 12 sides. To complete the octahedron, we'll need 6 of the 4-legged corners. The octahedron will take shape as we add straws to each of the corners. And there we have our octahedron. The octahedron has 12 sides. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. It also has 8 faces. 1, 2, 3, 4, 5, 6, 7, and 8. The octahedron is actually a combination of triangles and squares. You can see here is a triangle, whereas inside we have a square. This is very common in structures to have combinations of different geometric shapes. Our next geometric solid that we'll assemble will be the dodecahedron. The dodecahedron has 12 faces, and I'm going to let you count how many sides that it has when you assemble the dodecahedron. Let's build one real quick. Notice that the dodecahedron has 12 faces, and as you can see, it has a lot of sides. Now notice with the dodecahedron, I made the sides about half the length of a straw. Notice that each corner or vertex of this geometric solid has 3 spokes coming out from it, and each face is in the shape of a pentagon. In fact, the entire structure is made of pentagons. Let's do some testing like we did with some of our other structures. Let's apply a load to the top of the dodecahedron. It kind of just squashes. Why do you think that would be? The reason is the dodecahedron has none of these. The infamous triangle. Without the triangle, the structure has less strength. Let's go to our last solid geometric figure that we're going to look at. That would be the icosahedron. The icosahedron has 25 faces, and each corner or vertex of the icosahedron has 5 spokes coming from it. Let's learn how to do a 5-sided spoke. First of all, we make a familiar 3-sided spoke by folding it in half, wrapping one leg around the other at the midpoint, and we have our 3-legged spoke. Now we're going to take another pipe cleaner, and at the midpoint of that pipe cleaner we're going to wrap it around the vertex like that. And then we will bend back these long legs to the center. So that now we have 5 spokes on this corner. We'll need 12 of these vertices to build the icosahedron. I'm going to challenge you to build an icosahedron. When you do, it should look like this. This is a good-looking icosahedron. Once again, we use straws that were just half as long as the normal straw. Let's test the icosahedron like we did the dodecahedron. Let's put a load on the top of the icosahedron, and you can see, and if you do this, you'll feel that there's a lot more resistance to the load. Why do you think that would be? It's because of this. The mighty triangle. Notice in the icosahedron, there's triangles everywhere. This is a very stable structure. As we talked about earlier, the triangle is a basic building block for most construction. Of course, there are times when we need to use squares and rectangles in building construction. Squares are not very sturdy structures. If we apply a load to a square or to a rectangle, it will tend to change into a parallelogram. Let's see if we can turn this square into a stable structure. Now we have a square with a diagonal brace. This keeps the square from turning into a parallelogram. When we apply a force, it will not shift. Notice the square is 2 triangles. I have a homework assignment for you kids. Next time you're out driving with your folks, I want you to take a look at some of the bridges that you go across and see if you can find triangles in those bridges. Bridges are often made of triangles, like this bridge is. Triangles provide stability, and on the top of the bridge, we have a square, and it's broken into 2 triangles by a diagonal brace. This provides stability laterally, in other words, from side to side for the bridge. Bridges are used to get from one place to another, typically across a river or a canyon. In this case, we're going to go across 2 boxes. Again, we're going to apply a load to the top of our structure. And you can see that even though the bridge is not supported underneath the 2 boxes, it still has strength due to the triangles in the structure. So kids, while you're out and about looking for bridges and other structures, notice that there are triangles in all the structures. And remember that the triangle is what keeps the structures stable.